Welcome to this video. In this video, we will discuss the block diagram representation of a single area power system. So, in a single area power system, the different components involved are there will be generator and there will be load. Then the generator is driven by a turbine and turbine is controlled by a governor. So, there will be basically a generator plus load composite model. Okay. Then there will be a turbine model, then governor model. So, we have seen the individual derivations in the previous classes for these components. So I will give you a quick review of the different parts. So coming to the generator model, a generator is modeled by a first order transfer function like this, 1 by 2hs plus d, where h is the inertia constant of the generator and d is the load damping constant. So on the input side you have a summing block, and this input is change in mechanical power delta Pm, and this one is change in load power delta PL, and the output of this transfer function is change in frequency delta omega. So h is the inertia constant in seconds and d is the load damping constant in per unit. So what is the meaning of d? That is written here. Suppose d is equal to 1.5 per unit, then it means that for 1% change in frequency, load changes by 1.5%, because in the power system there are two types of loads. Some loads are frequency dependent, whereas some other loads are frequency independent or insensitive to change in frequency. For example, lighting loads are insensitive to frequency change, whereas motor loads, induction motor loads will draw power depending upon the frequency. When the frequency changes, the power consumed by the motor loads will also change. They are frequency dependent. So for a 1000 megawatt load with a D equal to 1.5, there will be a change in load by 1.5% for 1% change in frequency. So that calculation is shown here. There is a 1.5% change in load. Total load is 1000 megawatt. So 1.5% of 1000 divided by 1 for 1% change in frequency. Nominal frequency is assumed to be 50 Hz. So this is the value of D in megawatt per hertz. And in some problems you may need to convert D from one base to another base. So to do that, the equation is given here. If D is given in say 1000 megawatt, then if you want to change your base power to 800 megawatt, then you can do this calculation, 1.5 into old base by new base. Okay, 1000 by 800. Now coming to the total change in electrical power output of the generator, there are two components. One is due to the frequency independent loads, delta PL, or these are maybe due to lighting loads. So some loads will change which is independent of frequency, and that is denoted by this term, whereas some other loads will depend upon frequency. When there is a change in frequency by delta omega, their power consumption will change by D times delta omega, as per the definition of D mentioned before. So this total sum of these two components will contribute towards the total electrical power output change. So delta P, total electrical power output change in the generator, will be equal to change in load power due to the frequency insensitive loads plus change in load power due to the frequency sensitive loads. Then a composite model will be something where you have n number of generators and the dot and loads. These loads are for analysis purpose. These loads are lumped to a single load, okay, a lumped load. Then the steady state frequency deviation can be shown to be equal to minus delta PL divided by sum of the reciprocals of the drop coefficients plus D, minus delta PL by 1 by R1 plus 1 by R2 plus etc. up to 1 by Rn plus D. So this can be represented by 1 by R equivalent. These R1, R2, R3 etc. are speed drop coefficients of the n number of generators in that power system. So we can write it like this. Then this 1 by R equivalent plus D term is denoted as beta, that is called a stiffness factor or frequency bias factor. Then how to derive this? Suppose we have a net change in load power by delta PL. Then in order to account for meet this load change, generation will change by an amount delta PG. But when your load changes by delta PL, your frequency will also change. So when frequency changes, frequency dependent loads will change. So that changes delta PD. So net change in load power, that is delta PL, will be equal to the change in generation power minus change in the frequency dependent loads. And delta PG from the speed drop governor equation, you can write change in generator power is equal to change in frequency delta F by R. And this, there is a negative sign here. Why? Because suppose your load increases, then when our load increases, frequency will decrease. Okay, when load increases, frequency will decrease. So frequency decreases, so delta F will be a negative value. But in order to meet the increase in load demand, your generation has to increase. So this negative sign will make the total quantity positive. Delta PG will be positive. Then coming to delta PD, delta PD is the frequency sensitive load, that is either d delta omega or d delta F. Okay, now we can substitute these terms here, and by doing the simplification, you can see that delta F, steady state frequency deviation, is given by negative of load change delta PL divided by 1 by R plus D. 1 by R plus D. R is the speed drop, governor drop, D is the load damping constant. Now coming to the turbine model is represented by a simple first order transfer function with time constant tau t. Okay, so delta PV is the change in valve input. Then delta PM is the change in mechanical power output of the turbine. This is a simplified model. Then coming to governor model, the change in power output of the governor delta PG is equal to difference between two components, that is delta P ref, which is due to the change in set power of the governor, and change in power due to frequency speed drop delta omega by R. This also we saw in the previous lecture. So now you can represent the speed governor action. There will be some delay in the speed governor action. When you give a command of delta PG to the speed governor, the governor will take a small amount of time to respond. So it is represented by a first order system with time constant tau g. So the governor mechanism will give a control signal to the valve operation delta PV. So delta PV is the output of the governor transfer function. Delta PG is its input. Now collecting all terms together, here delta P ref minus 1 by R into delta omega is delta PG. This equation is schematically represented here. Delta P ref minus 1 by R into delta omega is equal to delta PG. Then delta PG is put to turbine model, you will get the output delta PG. So we developed all the individual components. Now combining all blocks, you will get the block diagram representation of single area power system. So this is a block diagram representation of single area power system. Here you have delta P ref, which is the change in set power of the governor. Then there is a feedback signal coming, which is from the speed drop 1 by R into delta omega. Then you have this governor model. Then after the governor model, you will get delta PV, which is fed to the turbine model, that is first order transfer function. Then from the turbine model, you will get delta PM, that is fed to the load generator plus load model to give delta omega. So this is the block diagram representation of single area power system. So we will do numerical problems based on this in the next video. Thank you.